38 is a constant. Same thing. I have a constant times a function. How do I differentiate this? How do I differentiate natural log?
1 over the function times the function product.
Very good. And now I look. 4,500, 7,500 minus p, and the same thing, 4,500 over 7,500 minus p. And now again, be careful if you're using the quotient rule in that step. Okay, so let's do this together. Of course, 38 will stay. This I have to flip because it's a fraction, which is 1 over 1 over this. So I have 7,500 minus p over 4,500. And now I square the denominator. I differentiate the numerator, which is 0, times the denominator, so I still get 0, minus the top.
Can you scoot your paper up just a little bit?
Oh, yeah. Sorry. Thank you. Are we okay? So we copy 38. I flip this fraction. I differentiate the top, but I get 0. 0 times the denominator, this is 0. And then minus the numerator times the denominator prime. Can anyone give us the denominator prime so I can put it here?
-1.
Brilliant. Thank you very much. Okay, luckily, look at that. Yay! So we have 38 over 4,500. Oh, no, never mind. I'll write it again. And 4,500 and 7,500 minus p. So these functions, as you've noticed, they clean up very nicely. So these will go away. And then I have 38 over 7,500 minus p. This is where I plug in 5,000. So t prime of p equals 38 over 5,000. 7,500 minus 5,000, 2,500. I will plug this in. So 38 divided by 2,500. So 0.0152. And I know you're going to give me 2 measurement units. And this is the rate of change at that moment when the population is, oh, sorry. I need to write in here 5,000, sorry. Nobody understands that. And we need 2 measurement units, one for the y variable and the other one for the x variable. The y variable is measured in
months.
Yes. And the x variable is measured in?
Population, people?
Yes, individuals.
Individuals.
Yes, population. Number, yep. Now, part B, last part here. What is the population of birds after 5 years? What is given in the question, and what do we need to do?
And plug it into the 38 over 7,500 minus 8. No, wait, because it's time. We have to set it equal. 5 equals.
Careful. Yes, 5 equals, I agree. But remember,
It has to be months, so we do 5.
Months,
yes.
60.
So 5 times 12 equals 38. Natural log 4,500 over 7,500 minus p. This is an algebra question. Has nothing to do with calculus, but let's do it. Okay, would you like to upload something so I can make sure that anything from here?
Can you go down a little bit?
Yes?
That's good, thank you.
So please upload that. I'll wait for a minute. And then we'll finish this algebra. And then we'll start chapter 3. That's all you need to cover from chapter 2. These first 3 sections.
Oh, can I, one more second? Oh, wait, from right here is perfect. Never mind.
What are we showing for the upload?
Just this page. One page. And then we'll start talking about critical numbers and how we obtain max min for functions. That's our next step. Do we need more time?
I'm hitting upload. I'm getting the picture to upload it right now.
Yes, please.
Okay.
Did you say this is all in chapter 2 that we're getting ready for the chapter 3?
Yes, this is it.
This
Only
one
the
is-
first 3 sections, yes. That's it.
Okay.
Okay, so what is the first step here? How do I solve this equation? Anyone?
Divide the constant.
Yes. Absolutely. So first we divide, so we have 60 divided by 38 equals natural log 4,500 over 7,500 minus p. Perfect. So now remember the base. The base of natural log is e. E raised to this number equals this fraction. E raised to this, ugly, equals this. 4,500 over 7,500 minus p. This is just a number. Forget about it. Just a simple number. I know it's bothering us the way it looks, but it's just a number. How do I solve this equation next?
Multiply both sides by 750.
Excellent. Or cross multiply. Exactly. So e to 60 over 38 times 7,500 minus p equals 4,500. 1 times 4,500 is here. This times this is here. Now I will divide by this. And then take care of that. So I have 7,500 minus p equals 4,500 over this number. Don't even bother with it. 60 over 38. And then subtract 7,500. And then multiply by -1 and plug it in. This is not easy to plug in the calculator. You have to be very careful. So let's take a look. Are we okay? Were you able to copy it?
So I have a question. I understand how we, like, you had the e over 60 to the 38 with the parentheses, like 7,500. minus E equals 4,500.
I divided both sides by this.
Okay, so then you divided E over to the other side.
No, I
E is
divided this side by this number, and I divided this side by this number.
Yes, I missed that part. I'm sorry.
No, I just don't want you to think that I'm moving it to the other side. That's all I was saying.
No,
you are correct.
No, I
Okay.
think that we divided it. It just took me a minute mentally to realize that that's what we did.
Yes. So to clean it up step by step, and then I subtracted 7,500, and then I multiplied both sides by -1. Or divide both by -1. This by -1, this by -1, this by -1. Same thing. Now we have to plug this in the graphing calculator and get P. Because the question was asking us to find, one more time, it said, what is the population of birds after 5 years? So let me share my screen. And okay, no, I don't need to do that. Okay, so we have 7,500 minus 4,500 divided by, so I like parentheses because again, I don't know what type of calculator you have, okay, and I put parentheses again, that's me. If you know that it works without some of these parentheses, I'm fine, but I don't trust anything here. We need to make sure that the parentheses are there. So this is the number of birds after 5 years. 6,572 birds. I can have 0.13 of a bird. So P equals 6,572 birds. That's it. Any questions? Okay, this is the end of chapter 3. I'm sorry, of course, I meant chapter 2. And we start chapter 3. Chapter 3 is a long chapter, and it deals with applications of differentiation. Applications of differentiation. And you can say, but what was this? What did you do today? Didn't you just do applications of differentiation? That's all this. That's all it is. Yes, true. Other, if you want to call it other. Applications of differentiation. I completely agree. More applications. Good. So, first of all, I would like to talk about something called critical number. That's our first step. What is a critical number? Well, a critical number can come from two different sources. One source is when the derivative of the function is 0. Once I solve this equation, if I find solutions, those solutions are critical numbers. If there are no solutions, there are no critical numbers coming from this source. But there is a second source, which is f prime of x is undefined. Careful, this is not the end here. For x values where f of x is defined, exists. If the function is not defined at 5, and the derivative is not defined at 5, the result is not a critical number. But if the function is defined at 5, but the derivative is not defined at 5, 5 will be a critical number. So critical numbers come from two sources. F prime has to be determined in both cases. Functions may have critical numbers coming from here and not from here. Functions may have critical numbers coming from this source but not this source. But there are functions that have critical numbers coming from both. So no matter what, I have to check both when I look at the critical numbers. Okay, so
Any
yes,
any x value in the prime function, if it were to cause it to equal 0, that would be a critical.
that makes it undefined, not equal to 0. You're talking
the top one.
the top one, yes. So when I solve this equation and I get x equals 5 and 10, then I will say these are critical numbers.
Okay, whatever that x value is, that would make
Correct.
it critical.
Here, when the first derivative is undefined for a value where the function is defined, I will say that is a critical number. Okay, so let's look at one example. And before we look at an example, my question is why? Why are you even talking about critical numbers? Why? What's the purpose? Well, the purpose is this. For now, I'm going to say a function has max min if it has critical number or numbers. However, critical numbers may or may not become max min. So what I'm saying is if a function doesn't have critical numbers, it can never have max min. If it has critical numbers, it's no guarantee that it has max min. But if it doesn't have critical numbers, it's a guarantee that it doesn't have max min. So again, what I'm saying is these critical numbers may or may not become max or min for the function. That's why we are looking at critical numbers. If it has no critical numbers, no max min. If it has critical numbers, an analysis will follow to see if they turn into max or min. Okay, so how many more minutes we have? 1. Okay, then I'm gonna stop. I'm just gonna start this problem and I'm gonna stop in 1 minute, promise. G of x equals x to the third minus 12x plus 5. So this is problem 19 on page 277. G prime of x is always defined. How do I know? Well, it's a polynomial function. 3x squared minus 12. It's a polynomial function. There are no critical numbers coming from G prime being undefined. What about from G prime being 0? Yes, because I have 3x squared minus 12 equals 0. I divide by 3 and I get x squared equals 4, so I get x equals plus or minus 2, critical numbers. And I'm stopping here. We're going to have more examples. This was just a warm-up on the issue. So critical numbers are absolutely critical for a function to have a max min. So this function is guaranteed to have a max min after the analysis of these critical numbers. But if these critical numbers don't change into a max min, but it will be guaranteed not to have max min if it didn't have any critical numbers, but it does. So when I solve this equation, I get plus or minus 2. This function has critical numbers. So it may have max min.